In this video, we'll explore RDD, Regression Discontinuity Design, one of the key methods in causal inference. Let's start with an example to build intuition. Suppose University A awards scholarships to freshmen who score 370 or above on the Korean CSAT, the Sunyom. A student who scored 369 and a student who scored 371 are just 2 points apart. The student above 370 receives the scholarship, the other does not. Yet we can't say there's a meaningful gap in ability between them. That 2-point difference is far more likely the result of luck or how they felt on test day. If we want to estimate the causal effect of the scholarship on academic achievement, on college GPA, what should we do? How about comparing exactly these two students? Since they differ by only 2 points, they are essentially equivalent in every way, except for whether they received the scholarship. That makes them the ideal comparison pair. This is the core idea of RDD, Regression Discontinuity Design. When treatment is assigned based on whether a continuous variable crosses a specific cutoff, we compare units just on either side of that cutoff to estimate the causal effect. Even without a randomized experiment, the situation near the cutoff naturally approximates random assignment, and RDD exploits that. Beyond this example, there are more real-world settings for RDD than you might expect. Scholarship eligibility, welfare benefit thresholds, legal drinking age, drug insurance coverage. Wherever a clear rule determines treatment, RDD is worth considering. RDD comes in two main forms, sharp RDD and fuzzy RDD. Sharp RDD is the case where treatment is fully determined by crossing the cutoff. For example, if every student who scores 370 or above is guaranteed a scholarship, that's sharp RDD. The graph shows treatment being perfectly determined at the 370-point cutoff. Fuzzy RDD, on the other hand, is the case where the cutoff affects the probability of treatment, but doesn't fully determine it. For example, if a student can score above 370 but still not apply for the scholarship, or fail a secondary review, that's fuzzy RDD. The treatment probability jumps at the cutoff, but it doesn't go from 0 to 1 completely, as you can see in the graph. This video focuses on sharp RDD. Fuzzy RDD will be covered in a separate video. For RDD to produce valid causal estimates, two important assumptions must hold. Let's use a new example, credit scores and mortgage loans. Suppose a credit score of 700 or above qualifies someone for a mortgage, and we want to estimate the causal effect of that loan on home purchase. The first is the continuity assumption. Both the expected home purchase rate without the loan and the expected rate with it must vary smoothly near the cutoff. No sudden jumps. If this holds, any sharp discontinuity in outcomes near the cutoff can only be attributed to the loan approval. What happens if this assumption breaks down? Suppose people with credit scores below 700 are eligible for public rental housing, meaning they don't need to buy a home. But the moment someone crosses 700, they become eligible for a mortgage and simultaneously lose their rental housing eligibility. In that case, we can't tell whether a rise in home purchase rates is because they can now get a loan or because they lost access to rental housing. The second assumption is local randomization. This means units must be unable to precisely manipulate their running variable value. For example, if a customer with a score in the 690s files a complaint with the financial regulator to force their score above 700, or if a bank officer intentionally adjusts a client's score, local randomization is violated. This is called manipulation, and it must be tested before any RDD analysis. To understand RDD, let's review 3 core concepts from causal inference. The first is the running variable. It's a continuous variable that determines treatment assignment, exam scores, age, income level. Each unit has a different value, and that value determines whether they receive treatment. As we discussed with the assumptions, units must not be able to manipulate this value to select into or out of treatment. The second is the cutoff, the threshold that determines treatment. In sharp RDD, units at or above the cutoff receive treatment and those below do not. The third is potential outcomes. Y1 is the GPA if the scholarship is received. Y0 is the GPA if it isn't. We can never observe both outcomes for the same student. A student who received the scholarship reveals only Y1. One who didn't reveals only Y0. The cells marked with a question mark are the counterfactuals. With 70 as the scholarship cutoff, RDD uses data near the cutoff to estimate the causal effect. Note that RDD does not estimate the counterfactual for a student who scored, say, 90 points. This is both a defining feature and at times a limitation of RDD. RDD estimates the treatment effect at the cutoff, known as late, the local average treatment effect. This is the expected outcome just to the right of the cutoff minus the expected outcome just to the left. If the assumptions we discussed hold, this difference is a pure causal effect. Given data, how do we estimate this in practice? We fit separate regression lines on each side of the cutoff, then measure the difference in their intercepts at the cutoff. To do this, we fit the following regression equation. In other words, fitting this equation gives us 2 lines, one on each side of the cutoff, each with its own slope and intercept. Let's walk through each parameter. Beta 0 is the expected outcome just below the cutoff, the intercept for the untreated side. Beta 2 is the key parameter. It's the jump in outcomes at the cutoff due to treatment, the treatment effect itself. Beta 1 is the slope for the untreated side. Beta 3 captures how much the slope changes on the treated side. The left limit at the cutoff is beta 0. The right limit is beta 0 plus beta 2. Therefore, the estimated treatment effect is simply the estimate of beta 2. Keep in mind, this is a local effect, limited to units near the cutoff. If the scholarship cutoff is 370 on the Korean CSAT, we cannot use RDD to learn how a scholarship would affect a student who scored 200. Now let's build intuition through a visualization. The graph gives us 3 layers of information: a scatter plot, regression lines, and the discontinuous jump. The scatter plot shows each student's exam score and college GPA. Students who received the scholarship and those who didn't are color-coded. The regression lines are fitted separately on the left and right of the cutoff. The 2 lines are estimated independently. The size of the discontinuous jump is the treatment effect. We estimate it from the difference in intercepts between the 2 lines at the cutoff. The core of RDD estimation is visually confirming how the regression lines differ on each side of the cutoff. But there are a few important things to keep in mind when reading this graph. As we keep emphasizing, causal interpretation holds only near the cutoff. The fact that students scoring around 340 and those scoring around 390 have different GPAs may reflect differences in ability, not the scholarship effect. Also, the slopes on the 2 sides are allowed to differ. That is, the regression lines for the treated and untreated groups can have different slopes. The relationship between exam score and GPA may vary depending on treatment status. Let's verify this with a simulation. We set the Korean CSAT scholarship cutoff at 370. With a true scholarship effect of 0.5 GPA points, we'll check whether RDD can recover this effect. We simulate data for 500 students. Korean CSAT scores are drawn uniformly between 340 and 400. GPA is generated as a function of the cutoff-centered score, plus the scholarship effect, plus some noise. We fit separate regression lines on the left and right of the cutoff. Then we estimate the treatment effect as the difference in intercepts at the cutoff. The results show a left intercept of approximately 2.02 and a right intercept of approximately 2.5. The estimated treatment effect is 0.48, close to the true effect of 0.5. This simulation confirms that by fitting separate regression lines on each side of the cutoff, RDD can successfully recover the treatment effect. Let's wrap up sharp RDD. When the running variable crosses the cutoff, treatment is fully determined. Under the continuity assumption near the cutoff, we can estimate the local treatment effect. The size of the jump at the cutoff, the estimate of beta 2, is that treatment effect. In reality though, some units above the cutoff may not receive treatment, and some below it may. That's fuzzy RDD. This video focused on sharp RDD. We'll cover fuzzy RDD in the next video.